In this section we shall study one of the most important theorems from all of calculus and also one of the most applied theorems and most useful theorems from all of calculus, and a very deep theorem, the so-called implicit function theorem. Let me start with some harmless motivating examples. First of all, we study a solution set of an equation again, namely the following: the set K consisting of all points x and y in R2 such that x squared plus y squared equals 1. So in other words, the norm of x, y is 1. This is equivalent to this equation. And the solution set is simply, this is not really a circle, but this would be a circle of radius 1 here in origin 0. So just a simple, this is also what you call the unit circle. Now, this circle, as a circle, this somehow, if you take a look at this shape, this is not like a subset, I mean, it's a subset of R2, but it doesn't look really two-dimensional. This is something which kind of very roughly looks one-dimensional. It's like, I mean, a line is something one-dimensional linear subspace of R2 or something. And this is also a bit like a line, but it's just curved, it's bent. So it's kind of intuitively looks like something one-dimensional. It's not two-dimensional in nature, very roughly. Now, the formally correct version to discuss this notion here, or to formalize this, would be the notion of a submanifold. Unfortunately, we don't have time in this course to denote to discuss the notion of submanifolds and or the theory of submanifolds, which is really beautiful, and I'm earning my money with discussing manifolds in my research. Now, anyway, this looks like something one-dimensional, and this idea, so it would be a one-dimensional submanifold of R2 would be the correct notion, but we can express this in a much simpler way, or we can discuss this easily. So the idea is the whole thing is a circle, so it's obviously nothing like a line. But if we take a small piece out of the circle, let's say we just take, I don't know, some point here, some x0, and we take the corresponding coordinate here, y0, and we just take a look at the part of this. So let's assume we take some interval x0 plus delta, x0 minus delta, for some small number delta, such that it's completely contained here in this part. So like this, and like this. If we only take a look at the part over here, this is in fact something one-dimensional because it's a graph. This is locally the graph of a map. This is just for over every point we have one y value. This is really what is a graph. Down here, it's another graph. So if we just restrict ourselves to looking at everything on here in the top right quadrant here, and in this part here, we can describe this locally, what you say, namely by just choosing some convenient interval here, locally as a graph. And this is the interesting property. So let's formalize this. So let x0, y0 be in K, and such that x0, the absolute value of x0 is smaller than 1, so we're not on the edge here, because on the edge, on these points here, there you couldn't do, because to both sides we have some, with every x value which is close to this edge here, we have two y values, one upstairs, one downstairs, so there this method doesn't work. So these points here are special. There we can't describe them as graphs, but we could do the other way. We could kind of imagine rotation by 90 degrees and just change the order of the variables and see this, like over here, as a function in as a graph over the y-axis here. This is a trick you could use there. I shall discuss this formally a bit more later. Now assume we have some of this x0 and we have delta bigger than 0 with the interval x0 minus delta, x0 plus delta, contained in the open interval minus 1, 1. Then the subset K0, which I define as all points in K, for which x is in the interval x0 minus delta, x0 plus delta. So this arc and this arc here in the diagram, so in this graph. Now here, sorry. This can be described as the union of these two arcs, and the first one is then given by, if you just take a look at this equation, x and the y coordinate is plus the square root of 1 minus x squared, where x is in x0 minus delta, x0 plus delta, and the lower arc here, this is just the same but with a minus. So x and minus 1 over minus x squared, where x is in the same interval. And both of them are graphs. This is this means K0 is the union of the graph of F1 and the graph of F2, which I shall define in a second. The graph F2, whoops, where F1 and F2 are both go from x0 minus delta, x0 plus delta to R. F1 of x is square root of 1 minus x squared. F2 is, of x is minus the square root of minus x squared, 1 minus x squared. So this is really how we can describe this as a union of two graphs. Now, we have seen at these points it doesn't work. And the question would, of course, does this work? Does this work in a more general setting? Like this is the solution set of some equation here. I mean, you could write this as if this is a function here in x and y, and this is something like f of x, y equals 1. So this is the solution set of some equation here. Now, if we would replace this expression, x squared plus y squared, by some general differentiable function there, does this approach still work? So let me ask the formal question here. Given a differentiable map f from R2 to R, and a certain fixed value c in R, and M shall denote the solution set, so x, y in R2 such that f of x, y equals c. So assume we have given this and we take a point, so I have said that we discuss locally here, so here in the neighborhood of that point we can describe this as this graph if we just ignore the lower half here. So given a certain point, x0, y0 in M, are there, it's like here the idea would be we need to take this interval here, and also here we need to restrict to a certain part, to a certain interval. And formally we would mean are there delta and epsilon bigger than 0, so that M intersected with the rectangle x0 minus delta, x0 plus delta times y0 minus epsilon, y0 plus epsilon. Such that, so corresponding here we would have, like, I don't know, from here to here, so this would be part of this rectangle. Over this rectangle, the intersection of the solution set with that rectangle is a graph, so that this is the graph of some map which we shall call G, where G is just some continuous map. So given, are there these such that this goes to y0 minus epsilon, y0 plus epsilon. So is there such a map? In general, the answer will be no, because you could imagine a curve which would, I don't know, look like this. So for example, there is also a solution set of some equation of this form which looks like this, like an infinity symbol, which is kind of crossing here. So if this was a solution set. If we then take a look at this origin here where the point's crossing, there's no way it looks like a graph, because in every, like if we open up to one of the two sides, we will always have two pre-images there. So there we would really have to improvise, and we could kind of, if we forget about this point here, we could do this here, but in this origin, because everything is meeting there, we can't just put this, write this nicely as a union of graphs in that sense. Now, here is the question, when can we do this? So what are general conditions for this? And this is precisely what's tackled by the implicit functional theorem, but in a more general way, because we do this for arbitrary dimensions. This is just for a subset of R2. We can do a similar thing for n-dimensional spaces, as we shall see below. Okay, so before we tackle the implicit functional theorem and also tackle questions like this, let me give you another problem, namely again a system of equations. And this also, in the beginning, it doesn't look like these two problems are related, but as we shall see later, they are. Namely, consider the following system of equations. This time we also have a parameter in there which we call lambda, and this time it's not the equations equals lambda or something, but we have lambda included in the left-hand side already, namely cosine of lambda x plus lambda squared e to the y equals 0, sine of lambda x plus e to the y xy equals 0. Okay, this again we shall denote by star. So this as a system in the variables x, y with lambda a parameter. So with parameter lambda in R. So the question is again, so if we view lambda as a constant, so just some fixed number, is there a solution of this system? And again, the answer would first be, no idea. There's no obvious way of how we could answer this question here at this point. So how to resolve this equation is almost impossible, I think. But there is another special case, so only in very special circumstances you can find a solution, and then the question is kind of, if we have a particular solution, if we kind of wiggle the parameter a little bit, can we just also find solutions that are close to the original solution? Namely, there's one particular part where you can see this, so take the special case of lambda equals 1, namely then we have just cosine of x plus e to the y, and here we have sine of x plus e to the y xy. Then you can find out, if you think about these things a little, x equals pi and y equals 0 would be a solution. Then we have here the cosine of pi, which is minus 1. Here we would have 1 times e to the 0, which is 1, so they add up to 0, fine. Here we would have the sine of pi, which is 0, and here it's e to the 0 times something times 0. So this would again be 0. So for this is a solution. This means if we have the parameter lambda equal to 1, so then we have a solution. So the question is then, so if we just modify the parameter a little, so if we take lambda to be in some small interval, 1 minus epsilon, 1 plus epsilon, for small epsilon bigger than 0, the question is, are there, first of all, continuous or differentiable or whatever functions x and y, 1 minus epsilon to 1 plus epsilon to r, such that lambda, x of lambda, y of lambda is a solution of the system. For all okay, so this is the idea here. So if we wiggle the parameter a little bit, we can wiggle the solutions, and they behave so nicely that if we modify the parameter, do the solutions then also move continuously or differentiably? I mean, everything here looks differentiable, so can we kind of define the solutions in a differentiable way? So it really depends as nice as we want on lambda. The good news is the answer will eventually be yes. In this situation, we can do this to this particular system, and this is due to the implicit function theorem, as we shall see later. And this can be also seen as a special case of this, because here in this expression, we had this equation x squared plus y squared equals 1, and we have identified this as graphs. And to identify these points and writing this y in terms of x in such a way, you can also say, and this is what you expressed this equation, we resolved this by x. Namely, we expressed y independence of x when we write it like this and like this. So locally, we can resolve this by x. Here, we have a similar system. So this is also one equation. Here we have 2 equations and 3 variables. There we have 1 equation and 2 variables, so it's a bit more complicated here. And here is the question, can we locally, near this particular point here, so 1 pi 0, can we resolve this system by y? By lambda. Can we resolve this system by lambda? So this again could be written as some map f, which has these as component functions equals 0. Can we then resolve this condition by lambda? So again, solving an equation in terms of some parameter dependency. So this is where the similarity lies. Now, can we find such a function? So we have the general framework is we have some condition, a function is equal to a constant, like as we've written here, and we want to write this as a graph. First of all, we want to have some nice property because there's something worth noting in the case that we have such representation, but before I need to introduce some notation for this purpose. So throughout this section, I fix some values m and n, so until further mention at least, with m strictly smaller than n. So this is the convention here for everything that's to come. Okay, so we can then also write, so if we have this, and just to make notation a bit more flexible, r to the n would be, of course, the same. This is just an n tuple of coordinates, and this is the same as taking first an n minus m tuple and then taking an m tuple of coordinates. So we will occasionally kind of split these as two, and so then we will write some element h of Rn. We will occasionally also write this as a pair, namely h1, h2, where h1 is in Rn minus m and h2 is in Rm. And this seems pretty pointless, but this will turn out to work nicely with the notation that we are going to use. Now, first of all, let U be an open subset of Rn, A be a point in U, and F from U to Rn, M, so from an open subset of Rn to Rm here, be differentiable in that point. Then, for all h, which is equal to h1, h2 in Rn. So then we can think about the following. If we take the differential of f and a and insert the vector h, so this is the same as the differential of f and a of this pair here, and this pair can be written as h1, 0 plus 0, comma h2, where this, of course, means we fill up all the remaining coordinates with 0. So the differential is linear, which means that this is the same as dfa of h1, 0 plus dfa of 0, h2. And this is kind of a nice decomposition of the differential, and because we will use this quite a lot, we will give it some particular notation. Define linear maps. The first one I call d1fa from Rn minus m to Rm. d1fa of h1 is just defined as this. So dfa of h1, 0. Okay, now I don't have space to define d2fa, so let me erase and then do this, but you can guess d2 is then this part here. Okay, d2fa is now a linear map from Rm to Rm. d2fa fa of some h is just defined as dfa of 0, comma h, where this is now the 0 vector in Rn minus m. And this means we have defined them in such a way that dfa applied to h1, comma h2, where this is in Rn minus m and this is in Rm. This is the same as d1fa of h1 plus d2fa of h2 for all h1, h2 in Rn minus m times Rm, which is just Rn. Whoops, yeah. Okay, so we can, oh, that's not a nice 2, that's better. Okay, so this is how we define these differentials here. Now, let's come back to this question of resolving equations by some expressions, namely in the following way. This is now some observation, which is already interesting in its own right, although it's a very special, very strong assumptions. So assume we have U1 an open subset of R n minus m, U2 in Rm be open, and assume that f from U1 times U2 to Rm. Assume we have this function and assume we have g from U1 to U2 such that there exists some fixed c in Rm with f of x comma g of x equals c for all x in U1. So this means that we have kind of resolved this equation f of xy equals 0 in this open subsets U1 and U2. We have resolved this equation by x, by finding such a g. Now, if we have differentiability here, so if g is differentiable in some point A, in some A in U1, and f is differentiable in the point A, g of A. And another condition now, this differential d2, or this part of the differential d2f, which is now mapped in A g of A, which is now a linear map from Rm to Rm. If this map is an isomorphism, we will discuss this condition later, then it turns out that the differential of g in A is the same as minus d2f in A g of A inverse, it's an isomorphism, composed with d1f in A g of A. Now this might look frightening, and yeah, this can be really used for computations by just using the matrices that are involved. But this is now interesting. So this is the linear map from Rn minus m to Rm. And this goes from Rm to Rm. So the whole thing goes from Rn minus m to Rm, which is correct because G is a map from a subset of Rn minus m to a subset of Rm. Now, what's so interesting about this formula? I mean, this looks quite awkward, but this has an interesting consequence. If we have resolved this here, if we can find such a differentiable function which resolves this equation in a nice way, then the differential of that function, and this is what we call, this is where the name comes from, an implicit function, because it's kind of implicitly defined by this condition here. We say we want a function which satisfies this condition. Instead of writing down an expression for g, we just say g is a function which fits in nicely. So it's implicitly defined, and this is why we call it an implicit function. Now, this implicit function, the differential of this function at the point A, and we don't know much about this function except that this works here. So not function map, actually, for to be precise, but the differential of this implicit map here is given in terms of the differential of f. This right-hand side doesn't involve g at all, except that we just take this one point, except we know this value, but this is not much. But we can compute the differential of g without knowing g. And that's quite an interesting observation here that it fits in here and that we will also use later on. Okay, the proof. So how can we see this? So first of all, it's basically simply the chain rule. Namely, we know that so f of x, g of x is equal to c for all x in U2. So by the chain rule, we can just derive both sides, both expressions in x. We derive both sides by a, and then we find that, let's start with this side. This here derived, this is a constant map, so you can easily see this is 0. So this is, almost trivial. This is now the differential of this here, and this can now be written as a composition. Namely, this is the same as f composed with the map, which is the identity in the first component, so this would be the identity on Rn minus m, time, or comma g, or not n minus m, sorry, on U1, and then g. And to derive this subsequently, so this is the derivative of this in A. Now, this is the differential of f in a g of a. And now by the chain rule, this composed with the derivative of what's in there. So composed with the map, which is the derivative of the identity is the identity. So this is the identity on Rn minus m this time. And here we have the differential of g. Differential of g in A. Yes, like this. Okay, but this means that if we insert some vector here, so for h in Rn minus m, so this we obtain, so 0 is the same as that expression, so df in a g of a of, and now this would be, the identity is just h, and there we would have d g a in h. And now this is in Rn minus m, this is in Rm, so we can now use this decomposition there, so this formalism there. So this is simply d1f a of the first part here, of in a g of a in h1 plus d2f in a g of a of dg a of h. Okay, and so this means if we just play around with this equation, d2f in a g of a of dga of h is the same as minus, so if we just subtract this first part, d1f in a g of a of h, and now we're almost there because this is already what we claimed. We just need to apply the inverse of d2. We know it's an isomorphism, so this is well defined. So apply d2f in a g of a to the minus 1 to both sides, and then we have the equation that we wanted. So this is just a nice application of the chain rule. So again, this is not a beautiful expression, I would say, but the differential of g can be only known, can be computed just from knowing f. And this is the cool fact here. Okay, so much about that. The problem is, of course, that if we kind of, this already assumes that we can resolve such an equation by a variable, and that the function by which we resolve this is already differentiable. But the question that the implicit functional theorem tackles is deeper. Namely, the question is, can we resolve this? Can we really do this? And so, without further ado, let me get to the implicit functional theorem at this point. So, theorem 13.9, the famous implicit function theorem. Okay, now the following setting. Now a bit more general, we have an open subset of Rn. We have f going from U to Rm, so lower dimension. We assume it's continuously differentiable. And assume we have some a comma b in U, where again we view a as an element of n minus m and b as an element of Rm. So we just apply this, this decomposition so far, the splitting into two as a pair here. So, and we put C to be f of AB. Now the question is, if we have the expression f of xy equals c for this particular c, can we then derive this resolving method? And the answer is we need some more conditions. Namely, we need the same condition that we had before. Namely, if d2f in AB, so this is again a map from Rm to Rm. So this second half of the differential, very roughly. If this is an isomorphism, then we can resolve this equation, and let me do this formally. Namely, then the following holds. We can kind of locally resolve it. It's always about local statements, meaning in small neighborhoods of the points there. So there exist open neighborhoods U1, which is a subset of Rn minus 1 of A and U2, which is a subset of Rm of B, such that, first of all, we are not leaving U, meaning U1 times U2 is a subset of U. And we can resolve this by the first expression here. So in other words, there exists G from U1 to U2, which is continuously differentiable. So that we have this resolving property, namely, first of all, so first point, f of x, g of x equals c for all x in U1. And secondly, if x, y is in U1 times U2, and it is a solution of this, with f of x, y equals c, so it also fulfills this equation, then y must be g of x. So this must already be this one. So we get all solutions in this local part here by just taking a look at the graph of g. So locally, the solution set here looks like the graph of g. Okay, I need a little more space for the proof, so maybe let me erase now and then we'll discuss how to prove this. And as I've mentioned before, we will prove this as an application of the inverse function theorem. I'm sorry, I've forgotten the last line of the statement, basically. Just this belongs still to the statement that moreover, and this is now basically just a straightforward consequence of the theorem before, namely in that situation, it holds that dGA is minus df in d2f in AB inverse composed with d1f in AB. Okay, so this is still part of the statement. Now for the proof. So I've told you we're going to use the inverse function theorem. Before we do so, assume without loss of generality that this point C that we are studying, so everything is kind of the solution set of f of x, y equals c, we assume that this is 0. This is not a loss of generality because otherwise consider the function which just subtracts c, namely f1 of xy is f of xy minus c. Then f of xy is c if and only if f1 of xy is 0, and all the properties stay because this is just shifting by something constant, so it doesn't affect differentiability or derivatives or anything. So this is something we can just assume here without loss of generality. Now, for the inverse function theorem, so how can we apply this? We construct an interesting map, or at least I find it interesting. Namely, we go from U, so the domain of f, which is a subset of Rn, to Rn minus m times Rm, which is Rn. And just to be explicit there with components, namely f of xy, where again this is the Rn minus m part, this is the Rm part. This shall be in the first component just x, and in the second component small f of xy, which is in Rm. So obviously this is differentiable or continuously differentiable since small f is. And for all x comma y in U and all h1 in Rn minus m and h2 in Rm, we want to compute the differential of f in that point. So df in the point x, y of h1 comma h2. So this is then by the differential of the components. So this would be here correspond to just projection to this first component. And if we take a look at the derivative, this would also just take the first component of this one. So the derivative would be h1. And there we would have df in xy of h1, h2 generally. Okay, so this is the general formula here. Yes, and okay, yes. Sorry, maybe simplify, modify this. This is, of course, again the same as H1 and D1 F in AB of H1 plus, using this formalism here, D2F in AB of H2. Okay, now, so what we need to apply the inverse functional theorem is that the differential is an isomorphism at some point, and that point is, of course, AB. Now, we need to show dFAB is an isomorphism, and since this is a linear map between Rn and Rn, it suffices to show that it's injective or that it's surjective, and we will show the surjectivity in this case. Namely, we let K1, K2 be an element of Rn, again, with respect to this decomposition, and we want to show that every such K1, K2 lies in the image of dF. Now, for this we compute. So since, and here it's the crucial point where we need the assumption here, since D2F of A in AB is an isomorphism, so this is here the crucial part where the assumption comes in. There exists some K3 in Rm such that D2F of in AB of K3 equals, and this now looks maybe a bit awkward, this is K2 minus D1F in AB of K1 minus D2F in AB, sorry, D2F in AB of K2. Okay, this is just some arbitrary vector, but since D2 is an isomorphism, it's surjective, so we can find some element which maps onto that. Okay, this is just chosen because it works out nicely, because now it turns out that dF in AB of the following vector, K1, and then K2 plus K3. This is the same as dF of AB of K1, K2 plus 0, K3. And since this is linear, we can just take first this and then dF evaluated on this. And so this here, we can just use this formula. This would be K1 D1F AB of K1 plus D2F in AB of K2. Okay, plus, and now this here, this would be in the first component just 0, because this is 0 here. And in the second component, we would get D2F of this here, and just by construction, by choice of our choice of K3, we get this here, K1 minus D2F AB of K2. Okay, and if you take a look at this, this is precisely built in such a way that this is precisely K1, K2. Okay, so for an arbitrary element of Rn, we have found some pre-image here under dF, which means dF in AB is surjective. And since it's a linear map from Rn to Rn, this means dF AB is an isomorphism. Okay, this means we can use the inverse function theorem, namely in the following way. So the inverse function theorem now tells us there exist open neighborhoods. First of all, U0 of, so U0 and V0, it's maybe like this, U0 in Rn of AB, and V0 in Rn of the image of AB, so capital F of AB, and if you take a look at how F is built up, this is just A comma C. such that, f is a bijection, so the restriction is a bijection. So f restricted to u0 as a map from u0 to v0 is bijective. And we also get f to the minus 1, which is now the inverse of this here, of course, so I don't write this down in detail. The inverse here is also continuously differentiable. This was the key point here in the inverse function theorem. Now, if you take a look at capital F here, so if you look at the way how it's built, if you see the x is just mapped to x here, so we don't know the inverse, but we know that the inverse must also keep this x here preserved. So in general, f to the minus 1 is of the following form. F to the minus 1 of xy must be also in the first component x, and then just some map which we don't know. Let's write this as h of xy, where h is continuously differentiable. So h from v0 to rm is continuously differentiable. We don't know about that. Okay. But by construction, now, if we start with some element of u0, v0 for xy in, in u0, we obtain, now, remember we want to solve the equation f of xy equals 0. Now, when does this happen? F of xy is equal to 0 if and only if, just by definition of capital F of xy is is x0. Here there's the value of f. Now, of course, we can just apply the inverse here. This means xy is equal to f to the minus 1 of x0. But this holds simply if f of h minus 1 is of this form, if y is equal to h of x0. We don't know this map h, but it has this property. Okay, so this holds if and only if this holds. So we're interested in solutions of this equation, although we don't know the function, but this, the map h, but this doesn't matter too much. Namely, first of all, since in particular, it must hold that h of a comma 0 is b, since this was one particular example there of, this was the particular case there. So h is continuous. It's continuously differentiable, but we only need at the moment that it's continuous. So from this you can derive, and now we're a bit sloppy, but this is something you can then show. There exist open neighborhoods u1, which is a subset of Rn minus 1 of A, and u2 subset of Rm of B, so because this here holds, such that, since we're, with, and we take them so small that u1 times u2 is still contained in our set u0 on which we were working here. So we can do this in such a way that h of x0 is in u2 for all x in u1. So if we kind of, we stay inside of u2 if we wiggle with x a bit around a. This is the idea here, and this follows from continuity. I will not fill in the details here. So this works. So this means we can define g from u1 to u2, our implicit function now, by just taking g of x as h of x0. And because of this equivalence, so by star, I had star before for the double star, sorry, star was the original equation system there. So by double star, by this equation we have that for xy in u1 times u2, it holds that f of xy is equal to 0 if and only if g of x equals y. And this is the crucial property. This is what we wanted to have. This is the decisive property here. First of all, every point g of x here, so f of g of x is 0 for all x. And if this is 0, then y must already be g of x. So this means locally f looks like the graph of g. This is what we wanted to show. And all that's left is the formula for the differential of a, which is up there. But this was the theorem that we had before. So formula for dga holds by theorem 13.8. And this proves the implicit function theorem. It's not an easy proof, I must admit. It's very technical, and I've also left away some details, but this is how you do it. Okay, and now we want to apply these things and want to see what the system of equations that we had before. So how can we apply the implicit function theorem to answer these questions about the resolving of a system of equations? Let me erase, and then we'll get to that.